All right, everybody. Good morning. Happy Monday. Um, so I guess assignment 5 is due, so hopefully that went. Hopefully at least it's over or soon to be over. So anyway, I guess hopefully able to figure that out. Anyway, so I do have a new assignment posted. I posted up last night on Web Campus. Now, I haven't set up the code grade to a testing script for a code grade auto tests yet. I'm going to have that probably set up sometime today. So I was able to get the PDF up and everything. Just I want to at least cover the assignment today to have the PDF up so you can at least start looking at that. And of course, I'll have the code grade set up soon. So that way you can sort of begin submitting, which this one shouldn't give you too much time to work on. Let me go ahead and sort of go over the assignment. Now we can go back to our actual lesson for today, which will be just quadratic probing. I think that's the next topic that we were on. Let's go ahead and screen. So here is the assignment. Let me just go ahead and sort of bring this up over here. Go. And there we are, assignment 6. So it's a bakery. I guess it could be any kind of establishment, it doesn't have to be a bakery, but I guess for this assignment, this was sort of another one, the ICPC competitive coding problems. I think the write-up for this had Wolfgang Puck's name used for a bakery, which I guess I could have put Wolfgang Puck in there. I mean, he reminds me of Klaus from American Dad, so it's a pretty cool character. But anyway, though, we'll just avoid that because I want to have tested inputs that cover other themes as well. But for now, we'll go ahead and just cover it as Wolfgang Puck's bakery. But then at some point, I may have some more test inputs, which will be other establishments to be covered. But anyway, this program, the rules are pretty simple. So we're going to be given sort of a set of different binders. Each binder will have a set of recipes. A recipe will have ingredients that needs to be used. And you want to compute the cost to compute every recipe. And you want to output all the recipes that fit within the budget of the binder. That's basically what this first two paragraphs really just kind of say. So of course, I'm going to, show you the test input file just to give you an idea of how you want to parse this. So let's go ahead and show that. So here's the file that I gave you guys. I put this up here. It's kind of not blocking this input paragraph. So I'm going to go ahead and zoom in on this a little bit. So in this file, every test input file you'll be given, you're going to first have a number up top, 2. For this instance, 2 really means that we're going to have 2 binders. So here's my first binder. So I'll go ahead and figure out how we can sort of compute that. But my second binder is going to be this one. Let's go ahead and just sort of get to how we actually do that. But this is going to tell us how many binders we have. So every binder has a name. So this first binder has the name My Favorite Cheesecake. You can tell this is not written by me because favorite is written incorrectly. But I guess for certain regions in the world, that is how it's spelled, but I guess not in America, but certain regions they spell favorite like that. So this is going to be the name of the binder. And then for this binder, we have these 3 numbers, like that. The first number tells you how many total ingredients we're going to use, 8. So we can see here, we're going to have 8 lines right there. So each line contains the ingredient name and its price. So you can see how a hash map will work. We have a string, a name, and maps to the price of that ingredient. So for this binder, we have 8 total ingredients. And then this 3 right there means there's going to be 3 recipes we're going to have to use for this binder. Or sorry, for this binder, 3 recipes. Yeah, I guess it makes sense. They're both kind of in Europe, although the British, they think that, they is for them, either you're incontinent or you're not incontinent. So if you're continental, that means you're a European continent, which is different from England for some reason. So even though it's similar to French, they always try to think that well, we're not incontinent because we're in England. So that's yeah, I found out so I knew that the phrase continental breakfast. I was like, what does that even mean, continental breakfast? Well, because for British, it's kind of more of a European style, which is on continents. So British is not continental. So it is what it is. They spell words incorrectly too in England. It's interesting. So then 3 will tell you how many recipes you're going to have for this binder. And then 100 tells you the budget you have for this binder. Okay, so we have 8 total ingredients. You're going to do 8 get lines basically, or actually not even get lines because it's going to be a string, white space, integer. So you can do your in file with the extraction operator because every line will contain 2 things. So you can even do that actually and set up a get line. So you can read in the string followed by integer, string, integer, and you're going to essentially put these into a hash map. Then at 3 is going to tell you how many recipes you're going to have in this binder. So the first recipe is called strawberry whipped cream. And then 2 right there tells you how many ingredients are going to be used for this recipe. So 2 means we're going to have 2 ingredients. Here's my first ingredient and second ingredient. And you want to compute the cost of this. So for this part right there, it tells you the ingredient name, followed by how many of that ingredient you want to use. So what's going to happen here is cream has the cost of 10, so 5 times 10, plus strawberry is 5, so plus 3 times 5. So we compute that cost, essentially. So the whole idea is that we don't want to have to search this list to find the cream's cost. You want to do the hash map to very quickly get the cost of this ingredient. So we have to map this to its cost, get the cost of it, multiply it by this number to add it to its own sum. And now we have another recipe, because remember for this binder we have 3. So the first one was this. Our second recipe will be this one. And that 3 means, well, we're going to have 3 ingredients used for that recipe. First ingredient, second, and third. So you have to compute the cost. So when we have our ingredients here for recipe, this number tells you how much of that ingredient we're going to use. So you have 6 sugars, 3 waters, 1 lemon juice. We want to compute its cost. And this up over here, this tells you the cost of each ingredient. So here we have sugar, so 6 times 4, then plus 3 times 0, because water has 0 cost. And then lemon juice is 1 times 3. We add that up, that's going to be a cost for this recipe. And the third recipe on this binder will be the secret cheesecake base. You have 5 as the number of ingredients used for this recipe. You have 5 lines, like that. And we compute the cost of that recipe. So then we're going to have our 3 recipes, and we have their names, and we're going to have their costs. So we're going to go ahead and output each recipe in sorted order. And we want to go ahead and output all of the recipes that we're able to compute. Let me go to the output portion at the very bottom here. Here's our program. So for our first binder, my favorite cheesecake, we output essentially the scrumptious caramel topping. That's going to be the cheapest recipe in that binder. The second cheapest will be strawberry whipped cream. And the third item is not printed out because that third item is going to make it so it'll exceed our budget. Because for this binder, this 100 right there tells you our budget for that binder. So the scrumptious caramel topping, strawberry whipped cream, those 2 together. So the cheapest one is scrumptious caramel topping. It's the cheapest recipe. So we're going to output them in sorted order. This is our cheapest. And our second cheapest. And these 2 together, if you add these 2 recipe costs together, it's under 100. Or at least it's not over 100. But then a third item, which would be the, let's see, which is the third one we have. I think it's the secret cheesecake. This is the most expensive one, but that would actually, if you add that to our total cost, that would be more than this binder's budget. So we're not going to output that in this case. So you output all the recipes until we finally don't hit, as long as we're within budget, we keep outputting. Once we go beyond budget, we stop outputting recipes for that binder. This is going to complete one whole binder. And after we're done with this, what happens now is the next line of input, that's going to essentially be our next binder's name, because we process each recipe in that first binder. And these numbers kind of tell us the story. We have 8 ingredients, 3 recipes, and every recipe has a number. So we can very easily determine how many lines you're going to read for every single recipe and every single binder. So just use these numbers to kind of help guide you in parsing this input file. And this next one, $1 million cakes, we have 3 ingredients. We're going to have 1 recipe in this binder, and that's going to be our budget. So here's our ingredients. Costly flour, 500. Gold is 4,500. Diamond is 5,000. And this is going to be our first recipe in our binder. They'll use 3 ingredients. Each ingredient, we're going to use 100 costly flours, 100 golds, and 100 diamonds. And if we compute this one recipe is going to go beyond that budget. So then we output no cakes can be made. We output that message to the screen because our cheapest sort of recipe in this binder is already beyond our budget. So that's basically what this program is all about. So the hash map is going to be used right here. So even in the second binder, I want to have this string. I want to insert it into my hash map, and then 500 is going to be its cost. The gold has cost 4,500, diamond costs 5,000. So when I have this recipe, I have costly flour. We have to find, well, how much does this flour cost? Because we're going to have 100 of them used in this recipe. So I don't want to have to linear search through this list to find costly flour. I want to go ahead and hash map to quickly retrieve the cost of the costly flour. I want to also quickly retrieve the cost of gold. I don't want to have to search. We just plug in the gold to a bracket operator, returns back the number 4,500. So I know what the cost of the gold is. I can multiply that to 100 to compute that sum for that recipe. So, and this one you can use vectors, unordered maps. So there's no memory leak issues going on here. No read memory issues because unordered map and vectors, as we know, they just work properly, right? So no need to worry about pointers and so forth. So not a hard assignment, really. Nothing, I mean, I guess only hard part's parsing the input. That's, I guess, challenging, but really that's kind of 135/202 kind of problem. So I think this should be kind of a nice little, I guess, dessert, figuratively speaking. Figuratively speaking, it's dessert kind of because, well, compared to assignment 4 and 5, this is like a little dessert right now. And I guess, we have all this dessert items right there. So it is kind of like dessert in a sense. So this is like a dessert for 302. Or, yeah, I guess we'll call it that. So, yeah, so yes, that's all there. Yes, so again, don't use a list. Use an unordered map to search everything up. And to store the items in a vector, you want to store all the recipes in a list and sort that list to output them in sorted order until like, let's say that cost is beyond the budget. A vector can be used if you want as well to store that. So, no pointers to worry about for this assignment. So I'll go ahead and I'll create more input files, more test files, because I don't want to have only one test file because since it's 30% of your grade is the output. I mean, I don't want to have just one output be 30%. So I have a couple of them. So if you let's say one of them doesn't work out correctly, well, then it's not going to be a 30% hit, I guess. So I'm going to try to make more input files. So I'm going to create more test cases, and I'll go ahead and I'll make the code grade for this. So we'll have this sort of, going. This one's actually, I think, due next Monday. I might not push this back because this one should not really take too much time. It should really not be something that's going to be really painful, I don't think. So I could give some time, but I really want to reserve time for assignments 7 and 8 and 9. I want to reserve more time for those because we have, about maybe 5, 6 weeks left in the semester. So I want to get this one done kind of quick and then have more time for our last few assignments, which could be a little bit more difficult. So this one, I don't want to push it back because that way we have less time for other assignments. This one should not really cause anything major. And also, the assignment will not use command line arguments to read in the file name. So I was able to finally, on CodeGrade, figure that out. So I'm able to use CodeGrade to read in the file name using cin. So you don't have to worry about command line arguments. You can read in the file name just like from 135, you see in the file name, and you pass that into your ifstream variable. So here we reprompt as long as the file is not valid. So this does not exist, this file, cakes and pies.txt, recipe.txt. This one does exist, so it opens up that input file. So no need to use command line arguments for this assignment. I was able to on CodeGrade figure this out, that part out. Yeah, assignment 7 is going to be making your own hash map. Yeah, I'll try to make that hash map not so bad. So I'm probably going to not use an array of linked lists because I think I've already kind of tortured you guys enough this semester. So it might use double hashing. I'll probably have two hash tables within the actual hash map class, but no array of linked lists. I guess I'll just sort of not do that because I think I've kind of done enough this semester. I'm gonna go and say I think I've done enough. Um, yeah, so that's pretty much it. So yeah, this part here goes over all the inputs. It's written right there, but of course I went over it here this video. And okay, so that's that. Any questions on the assignment at all? Maybe some questions, maybe not, but anyway, I'm going to end Discord. Definitely should turn that off. So okay, so I'm going to go ahead and I'm just going to sort of minimize this for now. I'm going to, I guess, continue from last time's content, which was pretty much sort of, hash maps. So we went over linear probing last time. The next thing I'm going to cover is going to be quadratic probing. But before I cover that, before I discuss this, I want to go over a few more topics actually. So the first thing I'm going to cover is resizing a hash map. So I'm going to actually just copy this. Actually, yeah, I'm going to keep this right there. I'm going to actually go over deletion first. That's what I'm going to do. So I'm going to erase this. I'll rewrite this later on. I just want to go over deletion and I want to go over resizing a hash table first and then go over quadratic probing afterwards. So just because. So I left in a very bad spot last time. So I was supposed to cover that next, but it's okay. I'm not too much all over the place really. So the first thing I'm going to cover actually will be deletion from a hash map. So let's suppose right now, I'm going to go ahead and take this table. I'm going to go ahead and just copy and paste it below so we can kind of refer to this table. Go ahead and copy all of this. Let's go ahead and copy that. Refer to deletion. So I'm going to just put this right here. All right. Try to remember what we actually did last time. So I believe, let me see, what was Wayne's, I'm going to try to remember what I did last time exactly. Perfect. Okay, so I have an idea. So let's go ahead now, and I'm going to remove Mary from this table. Let's say if I removed Mary. So I'm going to remove Mary from the table. So, okay, here's a way we can do this. I'm going to go ahead and just erase Mary from our table, just like that. I'm going to decrement items by 1 to make it 6. So let's see what happens with this. So what if, for example, I wanted to do the following. I want to go ahead and say, I'm going to say people. Now it's Ada equals people, um, Wayne, Wayne's World plus, let's say 5. Let's do that. So to recap how hash map works, we're going to first take the string Wayne, that's going to be our search key, and we're going to use a hash function on this. So the hash function will take the letter W, minus it by A, to give us the number 22 if you use ASCII subtraction. And then 22 multiplied by 10 will give us 2. Okay, index 2. There's a blank right there, right? So what's going to happen is the hash structure will think, oh, there's a blank element there. That means we have not inserted Wayne into our table yet. So let's go ahead and insert Wayne right there. Let's go ahead and do that. And the value will be 0, of course, for Wayne. So then it returns the value 0 plus 5 will give us 5. And then Ada has the index 0 because A minus A is 0, multiplied by 10 is 0. We're going to overwrite Ada as 19 to be 0. There's something definitely wrong with this. I mean, wasn't Wayne 23? And the answer is yes, Wayne is 23, but we didn't find Wayne. We found an empty spot for Wayne. So the problem is with using open addressing, if you try to do a deletion like this, the issue is whenever you do any kind of hash lookup, you always keep on, you map to a position and you do a probing structure, you do a probe sort of approach. If let's say at that position it's not blank, or the key that's already there is not the search key, we have to search and keep trying to find that element. In this case, linear probing is used to do this. So the problem right here is that, well, Wayne was at index 6. But what happened was index 2 became blank because we removed Mary from the table. So a blank means, oh, blank means that it's an empty spot, so Wayne has to go here. But wasn't Wayne index 6? Well, if Wayne's index 6, then there should be something at index 2, right? So something should be there, and the problem is nothing is actually there right now. So it goes straight to index 2 and inserts Wayne right there. But the problem here was that there was something there before, which was Mary was there before. And because Mary was there before, that's why Wayne is at index 6, because Mary was there earlier, and that caused a collision earlier, and that's why Wayne had to get remapped to index 6. But if you remove Mary from our table entirely, the problem is that that blank spot right there is going to be ambiguous because it'll think, oh, well, that blank means that nothing there, so make an entry there, which is not how you want to handle this because something might have been there before, and because there was something there before is the reason why other elements are mapped somewhere else. Because Mary was there before Wayne was inserted, that's why Wayne's at index 6. So a deletion like this is actually not a good idea. So the right way to delete something from a open addressing method is not to really wipe it out, but the proper way would be I'm going to copy and paste this entire thing again so we can redo this. So right there in red, that's sort of the bad way of doing this. I'm going to use blue next to kind of show the good way. So yes, blue is kind of, because red is always kind of, the color of, red is like stop at a stop line, so red is kind of always, try to do this, let's do this the smart way this time. So I'm going to now redo all this. I'm going to Mary from the table. This time I'm going to go ahead and write Mary here in blue. And Mary had the value, make sure I don't mess this up, 16. So it was 0, 16, like that. And we're going to keep 7 as our sort of our items amount, just because. So now, if I go ahead and the following code, I'll look up where Wayne is. Well, I'm going to go ahead and do the same hash function again. So indexed, so I first look at W minus A. We'll go to index, so it's going to give us 22 multiplied by 10 goes to index 2. Index 2 contains a deleted element, but we're going to treat that element right there, Mary, as it's deleted, but we're going to treat that as a collision. So from now on, 2 is going to be sort of wasted space. So 2 is going to be considered empty, but also will be considered as a collision if we ever do look at index 2. So that way, if let's say other elements are somewhere beyond 2 because there was something there earlier, we'll be able to now properly find it. So we do a deletion by, we don't really remove it, we just mark that spot as it's not there, but treat this as a collision. So now what would happen is, well, index 2 contains this dead weight element, so we're going to treat that as a collision. So we're going to have to go and increment I by 1, go to the next element, Xerxes, and this element is a collision with Wayne. Next element, Yasmin, then Ed, and then we found Wayne at index 6. Return 23. Add it with 5 will be 28, and we're going to assign 28 to Ada. It was 19, now Ada will be 28. So if you do a deletion on using sort of open addressing, so any type of linear probing, quadratic probing, any open addressing method, if you delete from your table, you want to really not delete it, but sort of mark it as deleted, but treat it as there's nothing there, but treat that as a collision. So even if I were to look up Mary in the future, index 2 contains Mary, don't treat that as if Mary is there. Just go ahead and sort of treat it as a collision and insert Mary to index 7 actually, if you were to look up Mary from this point on. So always treat this as a collision every single time from now on. So for the chaining mechanism, however, if we delete from our structure, we can simply deallocate that node, and that's it. Very easy to do that. But for open addressing, though, it can cause problems. So you have to make sure we don't really delete it, we just mark it as deleted. So now the problem is, well, now we have this spot wasted. So isn't that a bad thing? Yes, but at some point, though, you may have to resize your hash table. Let's go ahead and resize the following table right here. Let's resize this table, actually. The one that we have right here in front of us that we just recently removed Mary from. So I'm going to go ahead and go over sort of resizing. Let me go ahead and just put some note here for deletion, just in case. So deletion from a hash table. So if we use chaining, and just simply remove the node with that key, with the key value we want to delete from structure. That sounded like that was way too much writing, but really just simply just find that node with that matching key and delete it. Very simple for chaining. But for open addressing, however, well, we have to make sure we do the following. Just sort of mark that entry as removed and treat that element as a collision every time. That's how we do deletions for open addressing. This actually applies to quadratic probing, double hashing, all of the open addressing mechanisms. You have to do this approach to make sure that we sort of remove it. Now for chaining, it's going to remove that element from our table. Open addressing is not going to. However, when we resize the table, do not insert this element into the larger table. And then it's going to be deleted. And then it'll be officially deleted. So when we do a resize, then it's going to be officially removed from our table. So you simply just mark it as deleted, and we have to resize at some point. So resizing happens once the load factor becomes pretty high. So the items over table size, that ratio, that's our load factor essentially. Once that becomes kind of high, 50% or so, maybe even 40% even, then you want to go ahead and resize, which will essentially, we're not going to map that deleted element into our bigger table, which means it's been essentially removed. Let's go over resizing, I guess, right now. Our table, let's go over resizing now. Resize a hash table. So to do this, as always, we allocate a larger table, increase the table size, of course, and sort of hash all the elements from old table into the larger table. So you have to do it like this. So I'm going to now just sort of do an example and also show you why we can't just simply do a simple array resize like we do for regular dynamic arrays. So let me go ahead and copy this table here. We're going to go ahead and copy this. I'll set this as this. So blue really means the element is gone. I'm going to go ahead and copy this table. The perks of using OneNote. Just easily copy and paste stuff like this. So okay, so here's our table. I'm going to allocate a table of size 15. Let's go ahead and do that right here. That was a long, awkward silence. I apologize, but I'm just trying to make sure I don't mess this up. Okay. Silence has been averted. So now we're back to sort of, let me make sure I get the right number of elements. So 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Perfect. So let's go ahead. The indices here in red. Right. So for this new improved table, the items amount will be 0 at the moment, and table size will be 10. Just have to go and put the entire key value thing here. It's fine. This takes a little bit of time, but it's all right. That's okay though. Could copy and paste this, but I know if I try that, though, it's gonna take more time doing all that than actually just writing all this. So I'll just do it like this. Somehow I just know it's going to mess up the copying. It won't copy correctly. It'll put it wrong spot, and then some reason I'll have to restart OneNote because some reason I can't choose a marker color anymore, or just it's always something weird happens. I try to only copy only if I really absolutely have to copy when it's really necessary. So here I didn't have to. So okay. So the problem here is if I go ahead and take the elements in my tables, I put eta at 0, xerxes at 3, and so forth, there could be a possible issue. Because right now, in this bigger table, which I'm going to try to scroll this down a little bit, this bigger table has different table size amounts. It's supposed to be 15, not 10. So the problem here is that the elements could go somewhere else in this table because we're modding by a different amount this time, which means that it may not go to the same exact spot. So you want to make sure the elements are in the right spot with this new table size. Remember, we always mod our hash index value by a table size, so that way some elements might not be in the same spots anymore. So let's go ahead and just work this out. So I'm going to go ahead and first go to my first element in my table, which contains eta. Eta has the value a minus a is 0, multiplied by 15. Eta goes over here. It's the same as always. A just still goes to the same spot. The value is going to be, well, it was 0. It's going to be now 28. I'll put zeros across the board here just because. So initially, we would set all of our values to our default, which for integer types, default would be 0. Index 1 is empty. Index 2 contains Mary, but we removed Mary from our table. We marked it as deleted. So we're just not going to insert Mary into this position, into our table. So when we delete for unordered addressing and we do a resize, we just don't map that deleted element into our table. So after resizing, then it's going to be officially removed from our table. That's how we do it for open addressing. So Mary, we just simply will not insert because we marked it as deleted. So, okay, fine. Next element is Xerxes. So we use the same hash function, so x minus a, which will give us 23, and modify 15. So that's going to give us the value 8, I believe. So 8 is where we insert Xerxes. And it's going to have the value 30. Increment this counter by 1. The next element will be Yasmin. So Yasmin has the so y minus a, which can give us 24. Modify 15 will give us 9. Yasmin goes over here. And we'll overwrite this to be 24. Increment our count by 1. Next element in our table is Wayne. So Wayne has the value, let's say we have w minus a, which is going to be 22. Modify 15 will give us 7. So we're having the same issue again. We're having everything clustered together, but that's okay. And has a value 23 associated with Wayne. That index 7 is blank in our table, and STE, let's see, well, S has index, so S minus A is 18. Modify 15 will give us 3, so this has to go to index 3 in our table. Increment this count by 1. 2, 3, 4, 5. I'm missing another one. Oh, I'm missing Ed. Oh, I missed one. Before Wayne, Ed had to go in here first. Hopefully it doesn't mess anything up. I made a mistake, sorry. So Ed has a value 4. Modify, okay, so Ed would go over here actually. So I guess my mistake there. There we go. Because Ed has the E minus A will be 4, modify 15 will be 4, so Ed goes right there. So it didn't cause any issues. So we can see here that elements were kind of mapped in different spots. Yeah, a little bit different. So I guess because we have a different table size amount for this bigger table, so the hash function, in a sense, sort of is different for this table. So we can see here that if I were to just take in my elements, let's say, and literally just copy them, so Ada goes to 0, Xerxes goes to 3, Yasmin goes to 4 like that, what would happen is that when you apply this new hash function with this new table size, with this table, it would not be able to find those elements ever again, because Xerxes is index 8. So if let's say if 3 contains Xerxes, then it would actually, what would happen is it would jump to index 8, it would collide with STE, and then Xerxes would go to index 9. So we just lost Xerxes, basically. We lost the entry. So you have to rehash everything from your old table to your bigger table to resize. You can't just literally take elements from your small table and just copy them over like that, because then if you do a search, lookup, we're not going to look. So Xerxes is not going to be at index 3 in our table. We're going to look for index 8 in our table. And if there's something else already there, let's say STEs actually would have been there, correct? Well, then it would sort of collide and go to the next element, and it would insert Xerxes at index 9, which means that it's not going to look for index 3, which means we lost the entry. So you have to rehash everything in order to correctly maintain consistency and be able to still find the elements in your table. That's how you want to read. Now, of course, you can go ahead and deallocate the old table now. So, I mean, I could sort of give you an idea of this, but really it's not too crazy. So as long as your operator bracket function works, your hash mapping works, it's very simple to remap. And of course, you can actually use the this pointer and star this to make this actually work. So for example, what you could do is originally a table pointer that was inside of your class, you could have it point to this bigger table and create some temporary pointer that points to this old table and use this pointer to make that process work for you. You also can copy and paste the entire code for operator bracket and sort of modify it a little bit for this instance. But really, you just go with every element one by one in this table and just map it to his bigger table using the same hash function, but modify 15 instead, and that's all you'd have to do. So it's not really anything too drastic to resize and then deallocate at the end of this table. So as long as your bracket operator works, then this should not be any issue with resizing. So anyway, that was basically how we do a deletion and how we do a resize. And this deletion and resize applies to all open addressings. So double hashing and for quadratic probing, same concept. Just maybe different a little bit, but same overall conceptual. Same thing we have to do essentially. So that's that. So I can go ahead and talk about quadratic probing now, but any questions on anything before I go into quadratic probing? Okay, so I guess I'm going to zoom in on this, and now let's go over to our next topic, quadratic probing. I might not spend too much time on this because really it's not much different from linear probing, a little different, but not much more difficult really. Let's go ahead and just sort of discuss this one. Quadratic probing, I think I already wrote this earlier, but I removed it. Space rudder. So probing, basically same idea. It's going to heap sort. Yeah, so we're going to cover heaps probably most likely end of this week, and we'll cover it next week. So we'll cover heaps and heap sorts. So that would be on the exam, but it's not a very hard sorting algorithm. But yeah, that would be on the exam. So for quadratic probing, once again, we're going to essentially remap on a collision. Same idea as linear probing, except we're going to have, well, we're going to have a collision counter again. I, which is set 0 initially. And then we, of course, are going to increment I by 1 after each collision, and we use the following approach to remap. So you remap in the following way. We have our hash function as always, pass in the key plus I squared, and then mod that entire thing by table size. Once again, the whole point of modding by table size is to make sure we don't go beyond the bounds of our table. So all we're doing here is just simply doing it plus I squared if there is a collision. That's all we're essentially doing. So yeah, so it's going to try to space them out a little further. That's the whole purpose of this. So linear probing is very simple, but it's actually the problem with it is it does sort of have this clustering issue, whereas quadratic probing tries to spread them out a little bit. So the whole purpose is to try to have not much clustering, so we have less likely to have collisions in the future. That's kind of our goal. So let's go ahead now and do some examples of this. So just to kind of practice. So I'm again going to use a size 10 table. This over here on the side. 2, 3, 6, 7, 8, 9, 10. We'll have our indices here in red. We'll have our key value pairs, as always. Okay. Then our table, our items counter will be 0. And table size is 10, just like that. So again, we're going to, we'll declare our people. So we're going to have our, it's going to be hash map. Use strings and ints again. Let's call it people again, just like that. So this table right there in green is going to be our private member inside the people object, which is going to be our dynamic array of structs. So each element will be a key value. We're going to have a struct of table items, and each element has that key and value fields. So same idea, same hash function as well. And take the first letter minus a multiplied by table size. Same exact hash function again. Just this time we'll do a little different work. So let's go ahead and add elements into our table. So I'll say people, let's go ahead and go with Larry equals, I'll say 13. So then we're going to do the same process. So we're going to pass in Larry into our hash, into our bracket operator. We pass in Larry to our hash function. The hash function takes the letter L, minus it by A, which will give us the number 11, multiplied by 10 will give us 1. Index 1 is a blank spot, so we're going to go ahead and insert Larry right there. I'll put all the zeros here as well, just since we're already on that. All going to contain 0. We're going to overwrite the 0 to a 13. Remember what happens, you return this value by reference. So it's going to allow us in main to overwrite that value field for that element where Larry exists in this table. And of course, increment this items counter by 1. We just want to make sure we know how full our table is. So it's very full. We want to make sure that we sort of resize when our load factor becomes around maybe 50% or so. They want to, of course, resize our table within. And now let's go ahead and insert more elements into our structure. So I'm going to now use people, Vicky, and Vicky will have 7. So once again, we have to pass in Vicky into a bracket operator. We pass Vicky into a hash function. And for Vicky, the first letter is V, minus it by A will be 21. Multiplied by 10 will give us 1. Index 1 contains Larry, so we have a collision. So we're going to go ahead and take Vicky, which is going to be sort of that value 1, plus 1 squared, which will be 2. Multiplied by table size will give us 2, and index 2 in our table is blank. So we can go ahead and write Vicky right here. We're going to return this for this element in our table, return value by reference again, so that we can write 7 the value field and increment this items counter by 1. Just like that. And let's go ahead and look at another name here. So let's try people. Let's see, what kind of thing we got? Let's try Bella, like from Twilight. So anyway, so for Bella, we'll assign 11 for Bella. And we first take the, we go ahead and pass Bella into our hash function. And so B minus A will give us value 1. Multiplied by 10 will give us 1. So Bella maps to index 1, and we see we have a collision. We already have Larry there. So we're going to basically take the index 1 for Bella plus 1 squared, because we have a collision counter. Our collision counter is 1 at the moment, so 1 plus 1 squared will give us 2. modded by 10. Index 2 also has a name there, Vicky. We have a collision again. So our collision counter now becomes 2. So we have Bella 1 plus 2 squared, because it was first 1 plus 0 squared, then 1 plus 1 squared, then 1 plus 2 squared. So 1 plus 2 squared will be 1 plus 4, which will be 5. Modified by 10 will give us 5. Index 5 has a blank spot, so you go ahead and write Bella right there. And then we return a value field for Bella, which is this right there. And then we can assign 11 to it in main. And of course, increment our items counter by 1, like that. So we see here we have a little bit of separation. So our table is too small to really see any real big separations, but we can see here, as we have more collisions, we sort of spread everything apart a little bit more. So we try to spread things out a little bit. So we kind of did right there, because linear programming would have had 1, 2, and 3 all contain some elements. Here we have 3 and 4 are vacant, so we hopefully will not have too many collisions later on. But of course, in this example, we're going to pick a very bad distribution of keys, so they all end up having the index 1 every single time. So let's try another name over here. I guess Valerie equals, say, 19. So for Valerie, well, we have the name starts with a V, and then we subtract it by A, which will give us 21, modified by 10 gives us 1. Index 1 contains Larry. So we have a collision. So we have 1 plus 1 squared, which is 2, modified by 10, collision. 1 plus 2 squared, which is 4, modified by 10, collision. Okay, 1 plus 3 squared now. So 1 plus 9, which is 10, modified by 10 would give us 0. Index 0 is vacant, so you write Valerie over here. And we increment this count by 1. And then we're going to return the value field and assign 19 to it in main. Now, of course, the bigger table, it would have gone further down like that, but because the small table wrapped around back to the front. But you can kind of see the pattern that we do here. It's nothing really too fancy. And of course, if you want to look up something in our table, just to kind of recap how this works, I'll go ahead and I'll say people Valerie equals people Bella. Like that. Let's do an example of this. So how do we look up something? So same way as we insert, first have to find Bella in our table. So you go ahead and pass Bella into our hash function. So our hash function takes the letter B, minus it by A to give us the value 1. Modded by 10 is going to give us 1. 1 contains Larry, so you have a collision. So 1 plus 1 squared, which will be 2. Collision. 1 plus 2 squared, which will be 1 plus 4, which is 5. Modded by 10 is 5. And index 5 contains Bella. So we found Bella, so return 11. So same idea. All we do is either we keep on doing this until we find our key, or until we find a vacant spot, which means we have to insert and create a new entry into our table. Now we found Bella. Let's go ahead and find Valerie. So again, we have to go ahead and take the name Valerie, pass it to our hash function. Hash function takes the first letter V, minus it by A, which will give us the value 21. Modded by 10 would give us 1. So 1 contains Larry, so we have a collision. So 1 plus 1 squared, we have index 2, collision. 1 plus 2 squared, which is going to be 5, a collision. 1 plus 3 squared, which is 10, modded by 10 will give us 0. And we found Valerie index 0. Return a value field of Valerie, which is going to be reassigned the value 11. You return value by Valerie's value field by reference, which will allow us to reassign it in main using the following assignment operator, which is going to really not assign to our hash structure. It assigns to that value field within our hash structure. It assigns to Valerie's value field. So that's all there is to quadratic probing. Nothing too fancy there. Just that's all there is to it. So you just use this I squared instead. Could you repeat as to why the key in key plus I squared is 1? So is this for very, very last insertion or very, very last line right there, or because I guess for all these names, so we use a hash function every single time. So the first letter, let's say for Valerie, or let's say Bella even, sure. So Bella, so it's going to be B minus A, which gives us 1. And modified by 10 will give us 1. Then for V, for Valerie, V minus it by A for our hash function we've been using, V minus A gives us the value 21. Modified by 10 gives us 1. For L, for Larry, hash function is going to be L minus A, which is going to be 11. Modified by 10 will give us 1. So then initially I is going to be 0, so 1 plus 0 squared is going to be 1. And if you have a collision, then we're going to have 1 plus 1 squared, then 1 plus 2 squared, 1 plus 3 squared, and so forth. That's how that essentially works. It all happened to be just 1, yeah. I just picked a very bad case example just so we can see the complete spectrum of how quadratic probing works, but yeah. So anyway, same idea. If you have a collision, we just increment our counter by I by 1, and we use I squared to remap. That's the only difference. I kind of went through that pretty quick, but there's not much else to it really. So that's quadratic probing. So let's go ahead now and talk about double hashing. So we're almost done with hashing, actually. We're the very last sort of topic here. Very close. Now, of course, there's all kinds of things you can do with hashing. You can actually mix and match. You can use linear probing with chaining. You can do all kinds of, strange, stuff with hashing. I'm just covering the most basic ways of implementing it, but of course, you can do all kinds of stuff to try to somehow, separate your keys apart and so forth. But these are very basic. So for our assignment, we'll maybe use 2 tables so we'll kind of do a little bit of something different, from the this content, a little different, but based heavily on all of this. Let's go over double hashing next. So basically, double hashing is we're going to so we maintain, I guess, 2 hash functions. And really the structure we use, so we remap, or we can say we map to element in our table using the following method. So all we have to do is I'm going to go ahead and I'm going to write this here. So we maintain 2 hash functions. I'm going to go ahead and call these H1 and H2. That's what I'm going to call them just for now. And we're going to go ahead and say H1 of key plus I times H2 key modified table size. Where I, once again, where I is the collision counter and is initially set to 0. So we first just try to we use h1 of key, and we map it to index the first index essentially. So we go ahead and say h1 key like that. If a collision happens, then we're going to do h1 of key plus 1 times h2 key, and then modify table size. Every collision that happens, we increment I by 1, but using our second hash function instead to remap it. So it's a very basic way of doing double hashing. There's actually other ways we can really do this, but it's a very generic way of using double hashing. But we're having I as 0 initially, so we first go to index 1, and then index 1 plus index, so hash 1 plus hash 2, and then hash 1 plus 2 times hash 2, hash 1 plus 3 times hash 2, until finally we find the element in our table, or until we find a vacant spot. So really the same idea. So I guess I could do a very simple, quick example here, but nothing really different. Same concept, except a different way of remapping. That's all. Let's go ahead and just do a simple example of this just to, I guess, cover it. So we'll finish hashing, I guess, probably today, and then we'll talk about heaps and heap sort and so forth next time. So we're definitely making good time with content. So we'll have enough time to finish everything up this semester and enough time to give you roughly a few weeks on each assignment that we have. We have 3 more assignments left. We have assignments 7, 8, and 9. So definitely not going to be rushed at the end, which is really great. It's good to not be rushed at the end. For example, I'll have the following hash functions. I'm going to have hash function 1 of this key. It's going to simply just be one thing. I'm going to say just to lower. So we'll assume for right now we're going to use strings for our indices. So I'm going to say key index 0 minus a modded by table size. And my very creative hash function mechanism for hash function 2 to be very creative here to lower key index 1 minus a mod table size. Sure, why not? It works. It's a very boring hash functions, but we're going to focus mostly on just trying to understand the concept. I mean, I guess the hash functions, you could sort of do all kinds of research on this and use statistics and try to, based on different distribution of inputs, what's expected sort of spots, it would sort of insert elements into your hash table. But we'll keep that statistics part out for right now and just, go over the very basics of how to maintain a double hashing structure. So you have 2 hash functions instead of 1 this time. Okay, so I'm going to once again create our table. 2, 3, 6, 7, 8, 9. There's one more. And we'll have our key value pairs. I probably should just copy this templated table instead and reuse this over and over again. It's too late now because it's going to be the last table I'm going to draw, so there's no point doing that, but I should have done that earlier, but oh well now. It's too late. So anyway, there we go. Put the indices over here, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And again, of course, our tables or items will be again 0 and table size 10. Zoom out so we can see the hash functions as well. There we go. And then each value will again be set to 0. We're going to assume once again that we're going to use key for our strings, and values will be values will be integers. So default values will be zeros across the board. And of course, again, let me just make sure I did this correct up here. I did. So I'm going to go ahead and create my hash map object. Again, it'll be just string and int. It's people like that. So let's go ahead and insert elements. It's gonna be hard for me to come up with examples that will cause collisions, but let's just go ahead and just sort of cover this for right now. I'm gonna say, for now, I'm gonna say people, and I will insert, I guess, insert Nancy, I guess from Sid and Nancy. So I'm going to try, I'm gonna say 10. So I guess for Nancy, has the first letter is going to be N, minus it by 8 will give us 13, minus it by 10 will be 3, and there's no collision there, so we can go ahead and insert Nancy right there, increment our items counter by 1, return the value field for Nancy back to main, and in main we're going to assign 10 to the value field. And let's see. So I guess I'll insert Sid next. I guess it makes sense to insert Sid. And I'm going to go ahead and say 15. So for Sid, it's going to have the first letter is going to be, so S minus A will be 18, multiplied by 10 will be 8. So Sid goes right there. Return the value field, which will assign 15, just like that. There we go. So now what's going to happen is we're going to basically, let's try to have some collisions happen here. So I'm going to now, let's see, I'm going to pick Dan. Next. So I'm going to say Dan, and I'll say 13. I guess for Dan Marino, so 13. So we're going to pass in Dan to our hash function. So D has the value, so we're going to say D minus A, so we're going to have the hash value 3, multiplied by 10, and Nancy's already at index 3, so we have a collision. So what happens now is we're going to map Dan somewhere else using our method here. We're going to say, well, so we're going to say, okay, so our first hash function for Dan, so I'll put this over here. So H1 for Dan gives us the value 3. We take the H2 value for Dan now. So H2 value, so we're going to take the second letter, which is A, minus it by, oh, this causes an issue, so maybe I won't use Dan actually. This is actually a very bad hash structure. So okay, never mind, let's not use Dan. My mistake, because this is going to cause a problem. So, okay, never mind. Let's not use Dan. Sorry, Dan. Let's try to think of another one that's going to cause a collision. So I'm going to say, let's see if I can think of a good name. Dill. Fantastic name. Let's go with that name. Thank you. Like dill pickles from Rugrats. So we'll say we'll use dill. So let's go with dill. Thank you for the suggestion. So we're going to have dill is going to be used, and then the first letter D minus of A is going to be 3. We have a collision. So go ahead now, just sort of put both hash functions here to help us out. The dill has hash function hash 1 will be 3. For hash 2, with dill, so for I is going to be our second value. So I minus it by A. So for our second character in the name dill, we're going to take the I minus it by A, which will give us the number 8. Multiplied by 10 will give us 8. So we're going to try 3 plus 1 times 8, which will be 11. Multiplied by 10 will be 1. Index 1 contains a blank spot, so you put dill right there. Increment this counter by 1. Return the value field, which will assign 13 to it, like that. So all we have to do is keep on incrementing I by 1 after every collision, but we use sort of hash function 1 plus I times hash function 2. And we keep incrementing by I every time until we finally find a vacant spot, or until we finally find our element we're trying to look for. So same idea, except we use 2 hash functions instead of 1 hash function to do this. And the whole purpose of using two hash functions is to hopefully map everything out a little further. That's why we're doing this. So it gives a better probability of having elements mapped out. So let's see, do I have time for one more? I guess I might have time for one more insertion. So I'll try, let's see, I'll try, see, okay, I'll go with Inez. Yeah, that's a good name to go with. Let's go with that. I'm going to assign 18 to Inez, and then we're going to, okay, so we can first take the letter I. So let's go ahead and map out, let's go ahead and write our two hash functions out here. So hash function 1, make this, actually, say that. So it's going to give us, well, it's going to be first letter I minus it by A will give us the value 8, multiplied by 10 will be 8. And we have a collision, right? The index 8 contains SID, so we can't insert Inez right there. So we're going to go ahead and use our second hash function. So letter N minus it by A will give us 13, multiplied by 10 is going to be 3. So we're going to now do the following. So we tried I plus 0 times 3, which gave us 8. We had a collision. Then we try 8 plus 1 times 3 gives 11, multiplied by 10. Another collision happens right there. So then we're going to try, okay, fine. So we're going to try 8 plus 2 times 3. You always take the first hash function plus I times second hash function. So we tried I plus 0 times 3, collision. I plus 1 times 3, collision. I plus 2 times 3. So we're going to have I plus 6, which would be 14. Multiplied by 10 will be 4. Index 4 is blank. So Inez goes right there. Return a value field, which will assign 18 to it right there. We're going to increment our counter by 1 as well. So that's really how double hashing works. Now here we have some clustering, but the whole idea is to try to spread things apart a little further. So using a second hash function gives a better chance of having things spread out a little bit. That's the whole idea with double hashing. So of course you can mix and match some more. Oh, because Dan has the second hash function is going to be 0. So it would have been 3 plus 0 squared. So it would have been basically 3 plus I squared times 0. So what would have happened here is Dan's second hash function is 0 because the second letter is A minus A will be 0. So it would be constantly looping forever. We constantly remap index 3 every single time. So it would be essentially 3 plus I times 0. So 3 plus 1 times 0, 3 plus 2 times 0, 3 plus 3 times 0. So it would constantly keep on remapping to the same spot forever and ever like that. A better hash function is a way to get around this. This is a very terrible hash function, as you already can see. It's a terrible hash function. But, I mean, I guess for now, though, it's good enough just for example. But obviously, a better hash function is a better idea. Or maybe just never use zeros could be a better idea. But then index 0 in our table would be kind of obsolete. So one idea is never use zeros, or a better hash function would be a better approach. Or let's say a 0 is computed for a second hash, or so I guess second hash function made sure that it can't give a 0 value, I guess is sort of the simple workaround. Just made sure it's going to be maybe plus 1 or something, yeah. So that's probably a simple workaround right there. So either that or a better hash function is also a better idea. So I guess we're at time now. I guess I'm going to go ahead and end class for today. So we'll continue a little bit more on this next time. We'll cover heap structures next time. So I guess for now, take care. Stay safe. Thanks for watching, and I'll see you guys next time.